Hello, y'all. Welcome to lesson 49 of my DP chemistry curriculum. This is structure 2.2.11. This is an HL topic. We will be covering resonance structures that occur when there's more than one possible position for a double bond in a molecule. We'll be able to deduce resonance structures in molecules and ions. We're going to use the term delocalization to describe them as well. So without further ado, let's jump into resonance structures. So to do this, we have to consider a couple things. So one of the best ways is to look at an example. So let's look at ozone. Ozone, or trioxygen, is O3. So what I want you to do right now is take a moment to try and draw the structure of ozone. You can pause the video and come back. Otherwise, I'm going to start drawing it right now. Ozone looks a bit like this. I am doing this based off experience. However, if you want to learn how to draw these Lewis diagrams, there is another lesson earlier on called Lewis diagrams. So here is the structure for ozone. You'll notice that I've drawn it with a double bond and a single bond. However, you may have drawn it slightly differently. You may have drawn it with the double bond on the other side. And I'm here to tell you that that is quite all right. You may have even drawn the geometry a little different, but you probably shouldn't have. It should still be a bent molecule with an angle of less than 120 degrees. It's actually around 117 for the bond angle, as there are three sets of electrons. So this is going to be an electron domain of trigonal planar with the actual structure being bent. So this is what ozone looks like. Now, ozone in our atmosphere can be broken down by UV radiation. So if a certain wavelength of UV light hits ozone, it will break. But here's the weird thing. The energy required to break it, so energy required to break ozone is less than the oxygen-oxygen double bond, but it is more energy than the oxygen-oxygen single bond. So it takes more than what's required here, but less than what's required here. And so scientists struggled to figure out how that's possible. So it turns out that when we draw oxygen in these two possible ways, these actually imply this idea called resonance. What that means is that we will, one, use a fancy new type of arrow, this double-ended arrow, to represent that both of these are possible structures. In fact, this arrow means that these are possible resonance structures. And you may ask, well, what does that mean? Well, what that really means, and what we'll define here, is that the molecule delocalizes a pair of bonding electrons that spread evenly across both bonds. So what that means is that we have this pair of electrons right here that are actually delocalized. And because they're delocalized, they exist in both places at once. We can actually shorten this to what's called a hybrid structure. So our hybrid structure of ozone looks like this. And we use these dashed lines. So this is called a resonance hybrid structure. A couple things of note about the resonance hybrid structure that you've already noticed is we don't draw non-bonding electrons. And delocalized pair is drawn with dotted lines. And because it exists in both places, we draw it in both places. We still use the correct molecular geometry of bent, so we'll still draw it. So this is what it is to have a resonance structure, and this is also our resonance hybrid structure. So what we need to be able to do as students in the HLDP curriculum is be able to recognize when we would use these structures, as well as be able to recognize what these bonds look like. Furthermore, we need to understand the properties around them. So with that said, let's go ahead and figure out the properties first. We already learned from this little intro that the strength of the bond is different. The strength of the bond lies somewhere between the initial two bonds. So if we were to look at bond strength, and we created a chart from weak to strong, we can look at the oxygen-oxygen single bond being the weakest, then the oxygen-oxygen resonance hybrid bond being next strongest, and oxygen-oxygen double bond being the strongest. This is because hybrid structures share the property of both, resonance structures, resonance hybrid forms have what we call intermediate properties. So hybrid forms have intermediate properties, meaning properties that lie between the two forms they come from, somewhere in the middle. Another example of this is if we look at bond length, and we go from long to short, we still have the exact same flow chart. The single bond is very long, the hybrid bond is medium long, and the double bond is short. So this is our resonance structure, this is our hybrid structure, and this is how we classify their strengths. So we have one more way to discuss all of this, and that's with the idea of bond order. I'm going to change colors for this. Bond order. Bond order is a fancy way for us to differentiate and discuss differences in strength and length of covalent bonds. We do this really simply. A single bond has a bond order of 1. A double bond has a bond order of 2. A triple bond has a bond order of 3. Now, ozone has a bond order of 1.5. You might have been able to guess that because all of its bonds are in between a single and a double. So they're somewhere in between a single and a double, 1.5. And we actually have an equation to figure out bond order. So the equation for bond order is pretty simple. We just take the number of bonding electron pairs and we divide it by the number of resonant bonds. So we'll take an example and we'll learn how to do this. So what we're going to do is we're going to start with the example of carbonate. So you should know what carbonate is. If you haven't memorized this already from our list of polyatomic ions a while back, it is CO3 2-. If you do not know that off the top of your head, take a moment, pause the video, say it to yourself a couple times, write some post-its, stick them around your computer or whatever. Furthermore, we need to now draw carbonate. Carbonate is going to have resonance structures. So take a moment, pause the video, and try and draw all 3 resonance structures. That's a hint. Try and draw the resonant hybrid structure. And then after that, we'll go over bond order. So pause the video, and when you hit play, we'll be going over it right now. So carbonate has these 3 possible bonds with the location of the double bond being in 3 separate places. I'm going to be using lines to represent the electron pairs because I am quite lazy. We will use a double-ended arrow to represent that these are resonance structures. And so all we're doing is just moving the double bond along the chain and making sure that our electron pairs still match up, with lastly the double bond going at the bottom. So here are 3 resonance structures. Our resonant hybrid form simply looks like this. We're still going to crank that 2 minus on top. So now let's go over to order. So order, we notice that we have a possible 1, 2, 3, 4 bonding pairs. 1, 2, 3, 4. 1, 2, 3, 4. So our number of bonding pairs is 4. We'll divide that by the number of resonant bonds that can exist. So the resonant bonds are 1 here, 1 here, 1 here, 3. So it's going to be 4 over 3, which is fine. You can say your bond order as a fraction, or if you'd like, you can say 1.333 and just cut it off. I know it's infinite, but you don't have to. So this is our bond order for carbonate. This is all there is to resonance structures. We're going to do one more example. If you want to stick around for this example, cool. If you want to leave, you're fine to go. So this is our last one, HCOO minus. So this is the conjugate base of formic acid. So go ahead and first try and draw this. So we'll draw resonance structures. We'll draw the hybrid form. And we'll write the bond order. So pause the video, give it a shot. Otherwise, we're going over it right now. So I'm going to go through the whole pathway I look on how to draw this. I'm going to count my valence electrons, which is 1 plus 4 plus 6 plus 6 plus 1. That last one comes from the minus, which is going to be a total of 18. I'm going to identify that carbon is my central atom. I'm going to draw single bonds. And I only have 3 things here, so 3 single bonds. Then I've already used 6 electrons, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I notice that while hydrogen's complete with 2, oxygen has 8, carbon only has 6. So what I'm going to do is just move one of these over to form a double bond. And now I have my structure for this ion. I'm going to end it by putting a negative here. Now I notice that there are 2 possible positions for this double bond. It cannot go with hydrogen because hydrogen can only have 2 electrons. So this double bond would not exist here. The resonance can only be between these atoms of the same element. So I will go ahead and draw my resonance structure as such. CH double bond O, single bond O, with my minus charge. My hybrid structure is going to look like CH OO with my dots. There we go. Lastly, we're going to go over order. There are 3 possible bonds over 2 resonance bonds, so it's an order of 1.5. So hopefully you were able to follow along and do this yourself. Hopefully this helps you learn a little bit more about resonance structures, and have a great day.